Hello, ladies and gentlemen, and welcome to our first class in Physics 170 this semester. And since it's the first class, I thought we'd start at the very beginning, the very, very beginning, and say, what is science? What do we mean when we say that something is scientific, that someone is doing science? So the first thing that I want to make clear here is that science is a way of knowing. It's not just a set of facts. It isn't a collection of textbooks. It's a way of knowing. Often in our early education, in elementary school and middle school and high school, we're presented science as this massive mountain of facts. So it'll tell us, here are all the planets, here are their names, here's the order they're in. But science isn't a mountain of facts. Science is a way of getting those facts. It's a way of knowing about the natural world. And what makes those facts useful is that they came from this scientific way of knowing. That's why we can treat them as hard facts. So the body of knowledge that we get from science is a result of this particular way of knowing, this science. And this body of knowledge is iterative, so we learn things, we go back, study them in more detail, we learn new things, and we iterate on that, we change it, and then we go back and study again, we change it a little bit more, make it a little bit more detailed, a little bit more correct. And so it's malleable in this way. It's always changing, it's always evolving. And one thing that I really want to stress here is that science is open to revision. And what do we mean by that? We mean that any knowledge that's scientific is always open to being changed as we learn new facts. As we go and gather new facts about the natural world, we're always open to going back and changing what we know, fleshing out the details, making everything a little bit more accurate, restating things in a way to more correctly and more accurately reflect what we know about the natural world. So the process of science relies upon a few things. It relies upon many things, really, but I wanted to enumerate a few of the things that science relies upon here. And I've chosen these three things to talk about because I think they're important to us for this class. So science relies upon measurement and observation, reason and logic, and mathematics. So measurement and observation serves two vital functions in science. First, measurements and observations give us a starting point. They give us something to explain. We see things happen in the natural world, and we say, man, how did that happen? What causes that? When would it happen again? What kinds of things are required for it to happen in that way? And it also gives us clues about what explanations are viable. What kinds of things could potentially go into a good working explanation of how it happened. And second, when science explains the natural world, the explanations must involve ideas which can be tested by measurements and observations. Okay? So we observe something, it gives us something to study. We make some more measurements, we reason out some kind of explanation for how it happens, and then we carry that explanation out to its logical conclusion and say that if this explanation is true, these other things should also happen. We should also see things happen in this other way, in these other situations. And then we go test it. We go make observations in those other ways, in those other situations, and see that it does behave in the same way. If it doesn't, our explanation is no good. And that's one of the staples of science, is that when we go out and test, when we go out and observe, and things don't happen the way that our explanation says they should, the explanation is no good. We must come up with a new explanation. The second thing that I want to cover here is reason and logic. So reason and logic, these are just orderly ways of thinking that allow us to make firm, objective steps in our explanations and take firm, objective steps from what we observe to explanations of how those observations happened. And then finally, what I have listed here, mathematics. So the natural world happens to be largely made up of quantifiable processes, and mathematics is the study of quantities. It gives us the ability to describe these quantifiable processes and to predict these quantifiable processes. So science relies on measurement and observation, logic and reason, mathematics, but it's not completely free of assumptions. And this gets a little bit into philosophy of science, which is a whole field of its own. It's an incredibly interesting field. I would definitely recommend that anyone do reading on it. It's very interesting stuff to think about. But I wanted to do a very bird's eye view, very basic look at the assumptions that allow us to do science. So, after I show you these assumptions, I think we can agree that these are very limited assumptions to start from. They're very easy to take in. They're very reasonable assumptions to start from. And if we take even just these very simple assumptions, we can then work from there to build our entire factual understanding of the natural world by practicing science. It's really, really incredible what this process has produced throughout history. So let's start with the assumptions that we have in science. The first one, the external world exists. So in order to study the natural world, we have to first assume that it does exist, or it at least behaves as if it does exist. We have to assume that our experience when we observe the external world is not something that exists purely in our own being. The world isn't created from whole cloth only for our benefit. Or at least, even if it is, it behaves as if it does actually exist. So this is a pretty basic assumption. Just talking to me, we're kind of inherently assuming that the world exists. You assume that I exist, and I assume that you exist. So this is a basic assumption, but it is necessary for doing science. We do have to assume that the world exists. Our next one, that cause and effect is real. So the natural world is full of events, and science assumes that these events have mechanisms also within the natural world that cause them. So what we're really saying with this assumption is that events don't occur entirely unpredictably or in an entirely disorderly way or without causes in the natural world, in the physical world. We're saying that for every effect, there is actually a cause in the natural world that caused it. Or that events must have causes to occur. Events can't concur in a completely unpredictable, disorderly manner. And then the last assumption, and this one goes hand in hand with the assumption that cause and effect is real. We assume that the natural world can be used to learn about the natural world or to learn about these causes. So when we assume that cause and effect is real, we assume that the events in the natural world are caused by mechanisms that also exist in the natural world. But then we also assume that we can learn about these mechanisms by observing the natural world. So when we watch a mechanism unfold, or we make a particular observation, those observations are actually tied directly to what is actually happening in the natural world, which actually exists. So what we're saying here is that the natural world doesn't require some extra physical decoding manual to understand, and that we can observe it, we can use reason to build an understanding of the mechanisms that are occurring, that are causing events to unfold in the natural world, and then we can test that explanation of those mechanisms through further observations that are actually reflecting what is happening in the natural world. So these assumptions are all very simple, very basic assumptions to start with, and it turns out that just with these simple assumptions, we can start to do science, and we can use science to build out all of the things that we think as factual knowledge about the natural world, the universe that we live in. So let's go back to those topics that I told you science relies upon. So the first one here, reason and logic. Logic and reason are the foundations of intellectual thought. They're orderly ways of thinking that allow us to reach objective conclusions and objective explanations about the natural world. So by design, they're intended to operate to remove human bias and desire from an argument or from an explanation. We recognize science is done by humans, right? So bias always has an avenue to creep in. We always have bias, and it's always trying to snake its way in, okay? But the mechanism by which bias enters our explanations is by producing faulty reason or incorrect logic. It's not through a correct application of reason and logic that we get bias in our explanations. It's by allowing the bias to produce faulty versions of the reason and logic. So, reason. Reason is the power of comprehending, inferring, or thinking in orderly, rational ways. In more normal terms, we're engaged in reason when we're making sound, rational steps in thinking, and we're not relying upon bias or emotion to provide structural supports to our argument. So, as we look at the very structure of our arguments, A to B, B to C, at no point is emotion important in that structure. We kind of take this for granted, but it is actually a really important part of science. So science is only concerned with it, as we say, move from A to B, that the step from A to B is a rational step. It's not concerned with whether that step makes us comfortable or makes us happy or makes us sad. Only that the step is rational and that we move from those steps to create an explanation. So the second point here, logic. Logic is reasoning conducted or assessed according to strict principles of validity. Logic is designed so that it produces conclusions which must be true. I think of it like the math of arguments, and this math of arguments produces conclusions which must be true, provided that all of the premises are true. Philosophy departments often provide symbolic logic courses, and I would highly recommend any of these courses. These are wonderful tools for understanding how we build arguments, how we come to conclusions. And so I put a little example here of one form of logical argument. And it says, if A, then B. So anytime there's A, there is B. And then we say A. A is there. And so then our conclusion is that therefore B. And the way that logic works, the form of this argument is such that if this premise is true, if A then B, if that is always true, and A is true, then B must be true. Our conclusion must be true. So as long as our premises are correct, and oftentimes you'll see when people are arguing back and forth, what they're arguing is about the validity of a premise in a logical argument. So if both sides have a well-formed argument, if one side doesn't have a well-formed argument, all bets are off. But if both sides have a well-formed argument, often if you were to break down the structure of what people are arguing about, it's about the validity of a premise. Because logic is such that when the premises are true, the conclusion must be true. So if an argument follows a prescribed logical progression, then it must be true if you have to admit that all of the premises are true. So the conclusion must be true then. And logic oftentimes is the structure that we're using when we're using reason to figure things out, or reason to build explanations. Logic is often the structure of language that's used for this. So then we move on to measurement and observation. So measurements and observation provide the premises that we use in a scientific argument, and it also gives us a method of testing our conclusions. This is the one true hallmark of the scientific process. Above all else, science is a way of knowing that relies upon measurement and observation. And it requires that scientific explanations fit with all measurements and observations. This is, in a nutshell, science. This is the most important piece. So, measurements and observations can come from a few different sources. I gave a few examples here. We have controlled experiments. This is the best known and most classic source of scientific measurements. We limit influence of other variables in an attempt to measure just one thing. So you can imagine, say we have an explanation of gravity, and the explanation of gravity says if we're near the surface of the Earth, all objects should fall at the same rate. That's the way gravity works. And so we build a very controlled experiment. We go and we build a vacuum. We have a chamber with no air in it. And that allows us to eliminate air resistance. And we have something holding up a penny. We have something holding up a feather, or I don't know, perhaps a leaf, the way I drew it. And we create a device that drops both at the same time. So now we're eliminating the variable of dropping them at different times, right? And we observe what happens. Our theory says, gravity says they should fall at the same rate. And what happens in this vacuum? They do fall at the same rate. And they hit the bottom at the same time. Same exact time. And what does that tell us? That controlled experiment now gives us a piece of evidence that supports our theory of gravity. Okay, it supports our explanation of gravity for why things fall. So this is the most famous hallmark of science. We control variables to attempt to measure just one thing, and then we measure that one thing. Another source of measurement and observation is field observations. This one is another pretty well-known source. Think of Jane Goodall. She wanted to know about chimps, so she went out into the jungle and she observed chimps in their natural environment. Think of astronomers using telescopes to look at the sky. They can't control every variable in the sky, but they can point these telescopes at the sky and they can make lots of measurements. They can look at lots of different things, and then they can start to control things, and then they can start to figure things out, and they can use those observations to learn about the universe that we live in. Another method that's common in the social sciences is surveys. Surveys can be a method for investigating how people tend to think or act. Any one person, there's a lot of variability, but as we start to look at large groups of people, we can see trends. We can see how people most often think, how people most often act. We can see what kind of range there can be to people's thoughts or the way people will behave in similar situations. Surveys are a really common method in psychology and sociology, fields like that. And then the last one I have here, data mining. And with data mining, we can take large accumulations of measurements, even measurements that we originally used for something else, and we can examine overall trends. And by examining those overall trends, we can come up with new explanations, new theories for how those trends came to be, or what those trends are telling us, what they overall tell us about the natural world. And in science, there are many ways to observe the natural world. These are just a few examples, but there are many ways that we can draw some useful conclusions about how the natural world works. And the real key at the end of all this with measurement and observation is once we do come up with an explanation in science, it has to be testable. We have to say at the end, okay, I have this explanation, and if you went out and looked at this thing, it would turn out this way. And then we go out and look at that thing and see if it turns out that way. And if it does, that's support for the explanation. If it doesn't, we throw the explanation out. Explanations always gather support. We never consider them absolutely proven in the mathematical sense, but once they prove that something's wrong, they're no good. There's at least some set of conditions that they're no good for. So generally what we do is we go out and we use measurement and observation to disprove things. So as we talk about measurement and observation, I want to talk about a couple concepts here. Accuracy versus precision. When we make measurements, we're trying to put a quantity on some concept. So for example, we have a concept of the length of some object. That's some abstract concept that we have. And we measure that length to put a magnitude or put a value on that concept. Okay? The thing is 5 centimeters long. Our measurement will never be a completely perfect representation of the quantity in the natural world. So for example, think of if I use, say, a ruler, I can only go down to, I don't know, the smallest markings on the ruler, or half of the smallest markings. I can't be any more precise about my measurement than that, right? And that brings us to the idea that we can't have a perfect measurement of the natural world brings us to these two ideas of accuracy and precision. So these describe how far off we are from that perfect measurement or from the actual value that exists in the natural world. So the first is accuracy. Accuracy tells us how close our measurement is to the actual value in the natural world, or often how close our average measurement is to the actual value in the natural world. Because you almost always take a number of measurements. You take many measurements when you want to go out and find something, and you want to go out and test something. You take many measurements, and the average is ideally centered on the actual value, right? But there can be some difference between the two. And accuracy tends to be lowered by systematic errors. And systematic errors are problems with the experiment that always skew results in the same way. So, as a simple example for this, think if you had a ruler, but that ruler was missing the first inch. So every time you measure something, you measure it an inch too long. So everything that's actually 6 inches, your ruler's telling you it's 7 because that first inch of the ruler is missing. That's a systematic error. It skews everything to be a little bit too long. And that systematic error would lower your accuracy. Your distance from the actual value of the thing in the real world is off because of this systematic error. And every time you measure using this method, this ruler for measurement, you're going to be off by that much. Okay? Then we have precision. Precision is how much uncertainty or variation is in your measurements. Okay? Precision tends to be lowered by random errors and by small sample sizes. So when we talk about small sample sizes, we take many measurements, and the precision of those measurements, if you think of the spread. So think if I had a wide spread of data. Okay? I have all these little points. And I go out and I measure, and I only sample 2 of them. Okay? Just maybe these 2. I don't really have very good information about how broad my spread is, how big the total spread is. And if you think if each time I measured, I could get some random point in this potential spread of data, if I keep taking measurements, if I keep adding measurements, I keep getting a better and better idea of what this spread actually is, okay? So that's what we say when we say our uncertainty is affected by small sample sizes. If I only measure a couple of these points, it's really hard to tell how big of a spread I have in my data when I go take these measurements. As I measure more and more points, if each one is kind of randomly picked from this possible data set, I have a better and better idea. I have more and more confidence about how broad this spread actually is, okay? Because I'm more fully sampling it. I'm testing more of the possible outcomes. And then the other thing that can cause a loss in precision is random errors. And this is the thing I really want to focus on here. Random errors are experimental shortcomings that cause each individual measurement to be off by a random amount. So think of, as an example, you're timing something with a stopwatch. So you won't be able to perfectly stop the stopwatch at the end of whatever event you're timing. But each time you try, how early or late you are in stopping the stopwatch is a pretty random thing, right? You're not going to be early every time. You're not going to be late every time. If you're trying to get it right on the nose, you're going to kind of tend to randomly be a little early or a little late sometimes. And those kind of random errors that sneak in, like if you're using a stopwatch to time, I don't know, somebody's 40-yard dash, those kind of random errors that sneak in, those are what lower precision. So to illustrate these concepts, accuracy and precision, I want you to imagine that you have a target, like our little target here. And Imagine that you're going to shoot at it with a gun that has a scope on it, okay? And each time you shoot, you put the crosshairs of the scope directly on the bullseye, and then you shoot. So let's think about what your results could look like, okay? So, first idea, imagine every time we shoot, we take 4 shots. And imagine our shots look like this, okay? These little points are close, and they're close to the bullseye. So if we look at this, if I average these 4 points, I would have something that's right about on the bullseye, okay? And the grouping of these 4 points is very small, okay? If this represented a measurement, this is both accurate and precise. The average of all my measurements is near the bullseye. That makes it accurate. And the spread of the measurements is small. That makes it precise. Okay? Now, imagine if instead we took our 4 shots and our 4 shots looked something like this. So now I have a precise grouping, right? This is as close a group of 4 shots as it was when it was on the bullseye, right? But now they're very far. The average here is very far from the bullseye, okay? This is a low accuracy, high precision data set. I have a very small grouping, very little random error, but I'm very far from the target. And if I think about my example of shooting a gun with a scope on it, what this might tell me is that things are very close. My precision is very good. The shots are all close to each other. But there might be something wrong with the scope. Maybe the scope needs to be adjusted because every time I shoot, I'm off by this much, right? I'm off by this amount here. So I have a systematic error. The scope is not pointing at the right place. So when I think I'm aiming at the bullseye, it's actually aiming up here. So let's think about another example. And let's go the other way. Imagine I take my 4 shots and they look like this. Now these 4 shots, if I was to average them out, I'd have an average somewhere around the bullseye. So the accuracy on this is actually quite high. When we're talking about accuracy as we mean it in the scientific sense, this is obviously pretty bad shooting. But the accuracy in the scientific sense on this is high. But the precision, if I look at the group of these, it's very large. The precision is very low here. But you can see each time that I miss, it's in a different direction, right? There's some kind of random inaccuracy to this. Each time I miss, it just goes in a completely different direction. So at this point, then it doesn't seem like there's something just wrong with the scope, because I'm not missing in the same place every time. There's something that's randomly going wrong. Maybe I'm waving the gun around when I'm trying to shoot it, or maybe there's something that's different about each bullet, or maybe the wind is blowing, or and it's swirling or something, right? There's something that's not consistent here, and these random directions of missing tell me that I have some kind of large random error here, but that there's nothing in my experiment that's causing an error in accuracy, nothing that's causing a systematic error where everything is wrong in the same direction. Everything here is wrong in a different direction every time. So let's think about one more example here. So we get our accurate but not precise shots off of here. And imagine we had something more like this. Okay? Now, with this one, our precision is bad because our points are far apart, right? This is a very large area that our points cover. But also, if I averaged out these points, I would get something like, I don't know, this. or something. So it's also not accurate, okay? So in this case, my measurement has two problems. The first problem, there's random error that's causing me to miss in a different direction in every time. But then on top of that, there's some systematic error that's causing everything to be shifted off a little bit, the average to be shifted off by a certain amount. So in this case, it's neither accurate or precise. This is just bad, right? This is just a bad measurement. Okay, so moving on from measurement and observation, we go to the last thing that I told you science relies upon, and that's mathematics. Mathematics is the philosophy of quantities, and it's our language for describing quantifiable processes and quantifiable properties. Okay? Mathematics operates on proofs. A proof is like an explanation or an argument, but a proof requires that premises be already established proofs or absolute truths. And they follow purely logical arguments. So a mathematical proof always establishes an absolute truth. Okay, so these proofs establish a set of absolute truths. Everything that we know from mathematics must be the way that it is. Everything that's established by a proof must be true. So mathematics have been proven to be incredibly useful for describing the natural world. And this is because the natural world has so many quantifiable properties. If that didn't happen to be the case, mathematics might not be useful. But because it is the case that the natural world has so many quantifiable properties, and that the interactions of different quantities depend on the quantities or depend on other quantities, mathematics turns out to be very, very good at describing the natural world. And that is because the very essence of mathematics is to describe how quantities interact. So if you take the fact that the natural world just happens to be full of quantities, and then the fact that math describes how quantities interact, the two come together so that mathematics turns out to be excellent for representing and predicting the natural world. And that's how physics uses mathematics. We use mathematics to make incredibly accurate and incredibly precise predictions about the natural world and how it will behave. So then that gives us a little bit of a view, a little overview of what science is, a very bird's eye, quick view of what science is. So what is physics? Physics is generally described as the branch of science that's concerned with matter and energy and the interactions between those two things. So more colloquially, physics studies the basic rules that the universe follows. We use mathematics, reason, and logic to come up with explanations about how the physical world works, and we can use the mathematics that comes from those explanations to make incredibly accurate and precise predictions of how the world will behave. Okay? In reality, in the modern world, physics is a very broad field, and it covers a really wide range of topics that seem at first glance to have very little overlap. So I put a few pictures down here to represent some topics in physics. On the left here, we have solid-state physics that studies the makeup of materials and how we can make new materials, the actual structure that goes into materials. We have a picture here. This is a deep field view from the Hubble Space Telescope. There's a whole field of physics called cosmology that studies how the universe came into being and how it evolved into the state that it's in now. This picture is astounding. Normally when we look up into the sky, we think to see little dots are all stars. But as we look at this, almost all of these little points of light, all these little different colors and dots, these are all galaxies. So as we look out there, we see that space is absolutely lousy with galaxies. There's galaxies everywhere. There's a ton of them. This is a fascinating field and an incredible picture just to even look at and think about in a conceptual sense. Just galaxies upon galaxies, all equal to our own, all similar to our own. And then I have here a picture of a collision in the Large Hadron Collider. This is from a whole field called particle physics, and that studies the building blocks of everything in the universe. It goes right down to the elementary particles, the particles that aren't even made up of other particles anymore. They're the very basis, the smallest Legos that build up everything that we have in the universe. It's a fascinating field. And then I have on the right here a picture of the sun and a huge eruption blasting out a coronal mass ejection from the sun. And this is from the field that I study. This is from heliophysics. And that studies space radiation and space weather, how these eruptions from the sun can disturb the Earth and cause the magnetic field of the Earth to change, and how it can expose us to different amounts of radiation or affect power grids and things like that. And all of these fields cover just a vast array of topics. And this is just a drop, just a skimming of the surface of all the things that physics covers. But all of these things, understanding all of these things, it always starts with a course just like this one, where we start with the very basic tools and we start with the most basic principles of physics so that we can use these to build on everything else as we go forward in the study of the field. So before we go forward in this class, I want to cover one last thing, and that's about physics and mathematics. So as I said before, mathematics has proven to be an extremely important tool for practicing physics and for doing science in general. And you will have to be comfortable with using math in order to practice and understand physics. That is just a reality of the situation. And with that said, there are a couple of conceptual ideas, very conceptual ideas, that I just want to cover briefly here, just to get us off on the right foot as we go forward in this course. So the first one is, what is an equal sign? And put simply, an equal sign tells you that two things have the same value. And oftentimes in our early education, when we're in elementary school, when we're in middle school, we see things that maybe look like this. Okay? So we see this, and the way this is presented is that an equal sign tells you there's work to be done. There's something to solve. There's something for you to finish, right? But that's not really what the equal sign is telling us. What's actually telling us there's work to be done here is the blank on the other side of the equal sign. An equal sign, it doesn't like this blank on the other side. What this really looks like is we put the other side in. And this is what an equal sign is really about. It's telling us that these two things, what's on this side of the equal sign and what's on this side of the equal sign, they're the same. Okay? So that's telling us this idea, this quantity of 3, and we have this quantity of 4, and then we have this operation in between them. And this operation, addition, this tells us how the 3 and the 4 interact, right? And we know, this is a simple one, but we have these 3 things, we have these 4 things, we have the way they interact, and we know that what that means is that in the end, there's 7 things, okay? And in the end, we know that a 3 things plus a 4 things is the same as having a 7 things, okay? So, with that said, what does an equation tell us? An equation tells us that two quantities have the same value, right? That's what we covered with the equal sign. But then by extension, it tells us what quantities are important for the prediction of some quantity that we care about, okay? So in physics, you're going to become very familiar with an equation that looks like this, okay? F equals ma. What this is telling us, what this equation tells us, is that the quantity F depends upon the value of m and the value of A. Okay? And this notation means that M and A are multiplied, right? So what it's telling us, F depends upon M and A. And if I want to predict F, or if I want to calculate F, I multiply these two quantities. So it depends upon the product of M and A. And that's what an equation tells us. That's why an equation is important. Because then when I want to know the force, I can always find it by measuring the mass and the acceleration. Okay? If I want to know F, I can measure M and A, and I know how F depends on those things, so I can always calculate F. Okay? So it tells us what kinds of things a quantity depends on, and it tells us how it depends on those quantities. And this is really important for our understanding of physics and for our ability to predict the natural world. Okay? As we move forward in this course, we'll combine principles of physics with some fairly simple mathematical calculations to understand the universe that we live in.